specify the energy and the angular momentum, right? If I specify the energy and the angular momentum, then that uniquely specifies the trajectory. For example, if I started it out here with no momentum in either x or y, and it does, goes through the origin, comes back, how much angular momentum does it have? It's always once in a while good to think about balls rolling around and think about physics occasionally. Well, angular momentum is r cross p, right? In this case, the p is along r. It has no angular momentum. Angular momentum is 0. It's going through the origin, right? If I looked at this in the xy plane, the particle is going through the origin, right? It has to have some kind of motion in a plane. This is not x and p. This is x and y. In order to have angular momentum. So this is a part. On the other hand, if I set the particle moving around in a circle, it's all angular momentum. There's no radial momentum in that case. In fact, for example, the state that would have all of its energy in angular momentum and none of it in radial motion, well, that would have equal amounts in x and y. For example, suppose I have a trajectory which is, so suppose at t equals 0, so let's consider the following trajectory. Let me have equal amounts of energy, half of the energy, so I'm going to put the amplitude as a over 2. Okay? So the energy of this particle is just as it was before. Okay? But this particle is moving around in a circle, right? This particle has angular momentum. In fact, all of its motion is angular momentum. This trajectory has exactly the same energy as this trajectory. But it's a superposition of this guy and the guy that is in perspective going like this. So it's a superposition of two motions. One motion along the y-axis, one motion along the x-axis, with half the energy in this and half the energy in that. And 90 degrees out of phase with one another, right? So they're going like this. Right? And so the thing moves in a circle. See that? So this particle, this trajectory is degenerate with that trajectory. Motion along x or motion along y. Is that clear? It has exactly the same energy. The energies of the system. Notice, and this is something we're going to come back to in a moment, this has a kind of interesting form if I write this as the real part of a complex amplitude. So that's e to the minus I omega t x plus a, and then I e to the minus I omega t y. So that's cosine, and that's sine, right? So this is equal to a times the real part of x plus iy over root 2 e to the minus I t. A vector going around in a circle is naturally defined by this complex vector in complex space, right? This is a vector here that corresponds to motion in going around in a circle. This is a vector we're going to see over and over again. We already saw it earlier in the semester. It is the, if I do rotation about the z-axis by some angle, this vector is an eigenvector of rotation with eigenvalue e to the I rotation angle. So if I have a rotation operator that rotates x into x cos omega t, or cos theta ey, this is phi, and rotates y into ey cos phi plus r minus x sine phi. So that's a physical rotation by that angle. Then this vector acting on E plus is e to the minus phi plus. You see that? You have to plug all that in, right? Ex goes to that, and then you're going to get ex minus I sine phi, and then it's going to do that, etc. So this vector is an eigenvector of rotation around the z-axis, physical rotation around the z-axis. Now, so this is just classical physics, right? Balls roll around in a bowl. I don't know why when you talk about classical physics, you have to sound like you're a Christian pumpkin, but it sounds more interesting. Now let's talk about quantum mechanics. What we said last time was that what we saw here is that because of rotational symmetry, so rotational symmetry about the z-axis LZ is concerned. And what that tells us from quantum mechanics is that LZ is the generator of rotations around z-axis. So I can write a unitary operator acting on the Hilbert space such that the unitary transformation on the coordinates is what is a physical rotation. So this is a unitary transformation on the position operators associated with coordinates x and y that rotates those coordinates. And what is this operator? Well, it is the thing generated by LZ. E to the minus I phi LZ over H bar. That is the rotation operator that rotates you around the z-axis by an angle phi. Okay? And what is LZ? Well, there's lots of ways to look at it. LZ is, L is R cross P, so that's this. Remember, L is R cross P. Or, as we discussed last time, LZ, we can say, well, P phi, the momentum along the tangential direction in the position representation is H bar over I times the derivative with respect to that length. And that length is that. That's, remember when we have the momentum operator, it's a derivative with respect to the distance along that coordinate, right? And this is equal to LZ over rho, so LZ is H bar over I d by d phi. And that thus is clear that LZ generates displacements along the phi coordinate, which is what it means to be the generator of rotations. Okay? And it is thus obvious from this that the eigenfunctions of LZ are the ones that satisfy some d by d phi this guy. So H bar m. That's to say the eigenfunctions are just the plane waves with respect to phi, which are e to the I m phi. And then we can normalize them because phi goes from 0 to 2 pi. Right. So, what was I going to say here? Oh, yeah. So, let's go back to our 2D simple harmonic oscillator. And in the same way that I created a classical trajectory out of a superposition of motion along x and motion along y that were 90 degrees out of phase with one another, let's look at a state in Hilbert space, which is a superposition of one excitation along the x-axis and one excitation along the y-axis that are 90 degrees out of phase one another. So let's consider the state. So let's consider a state which has half of its probability where nx is 1 and ny is 0. And it's got half of its probability amplitude where it has one excitation along y and one excitation and no excitation along x. And I'm going to make it 90 degrees out of phase. Right? This state has one unit of excitation. It's degenerate with either of these. This is also an energy eigenstate. It's an energy eigenstate with energy eigenvalue h bar omega. But it's also an eigenstate of angular momentum. How can we see that? The others weren't. So how can we see that? Well, we could see that immediately if I write out the wave function. Let's write this out in position representation. This is the Hermite polynomial for 1x e to the minus x squared over 4, and then, right, so that's that. That was one excitation and no excitations. And then I have plus I over root 2 Hermite polynomial for 1 along y times that same Gaussian factor. You see that? Okay. Now the Hermite polynomial is some normalization constant times x or y. Right? It's linear.
Should that be negative x squared minus y squared?
It should be. That's supposed to be like that. Thank you. Absolutely. So, this wave function is some normalization constant. Then I have x plus iy over root 2 e to the minus rho squared over 4, where rho is the magnitude of square root of x squared plus y squared, right? You see what I did? All right, what about this? Well, let's look at cylindrical coordinates. Here's my vector, rho, in the xy plane. Phi is this angle. X is equal to rho cos theta. Y is equal to rho sine, phi. Okay, so this is cos phi plus I sine phi, opening the root 2 out here, times rho e to the minus rho squared over 4. And what's this? Well, that's e to the I phi. So this function, this eigenfunction, or this wave function, is an eigenfunction of angular momentum. Because we just said they are. And what is its eigenvalue?
What?
1 h bar omega. Yeah. So this is an this is a case where we superpose two eigenfunctions associated with x and y motion and got an eigenfunction of angular momentum. Okay? In fact, this is separable in terms of, as I wrote in the front board over there, as a radial wave function. Let's come back over here. There are eigenfunctions of the Hamiltonian that I won't throw chalk. I've done anger management. I don't know how long it'll last, but we'll see. Anyway, there are cases where we have eigenfunctions, radial eigenfunctions, and angular momentum eigenfunctions. And if there's degenerate space, these eigenfunctions must be generally, if there's degeneracies, superpositions of these. Okay? You will have a homework problem doing this ad nauseum soon. But the one last thing I wanted to emphasize about this is notice again, we see this combination, x plus iy, which were the eigenfunctions of rotation around. If this was x plus iy squared, right, this would have 2 units of angular momentum. around is the axis. I'm going to keep that in there, it's going to be important. All right. Good. Mechanics. Angular momentum. It's not just about abstract algebra anymore. But let's talk about abstract algebra now. We have this in mind. So what we discussed in last lecture is that because LZ is the generator, well, let me word it this way. So what we showed last time was that this operator is the generator of rotations in physical space about an axis. Let me finish. And so if this was the x direction, that would be Lx. Y direction, Ly. Z direction, or any direction in space. Okay? And thus, the operator e to the minus I theta n dot L hat over H bar is what? What does that operator do?
Rotates about 10 by
Exactly, thank you. So this is the rotation operator, I'll call it U, for an axis and an angle. This is rotation operator about axis n by angle theta. Okay. And given that for an infinitesimal rotation, infinitesimal rotation. So if I rotated some vector about an angle, about an axis and by infinitesimal delta theta on some vector, what I get is the vector plus a little amount along the direction of the cross product. We argued that last time. From that geometry, what that says is that if I look at an infinitesimal, a near unitary, I keep saying that, a near identity unitary, something which is a small amount, using the demand that this infinitesimal achieve this, that means that so by insisting that this unitary transformation on a vector operator is the vector plus delta theta n cross v. Okay? By insisting that, that tells us that vectors have a special commutation relation I'll write it out in component form. We proved this last time that Li Vj is I h bar, epsilon ijk vk, sum over k. That is to say, this is the definition of what we mean by a vector operator. A vector operator, something that is a vector in three-dimensional space, is something that satisfies these commutation relations because it rotates the right way. That's what we mean by a vector. Examples of vector operators: position operator, momentum operator. The components px, py, pz, x, y, and z commute with the components of angular momentum Lx, Ly, z. This way, you prove that in homework, right? Angular momentum is a vector. And that means this. So the components of angular momentum themselves don't commute with one another. And as we discussed, that is to say that rotations around different axes don't commute. And that's geometry, right? I did my little trick with my iPhone and, you know, I got the new iPhone. All right. So now, given this, which was derived and motivated by what a rotation means in three-dimensional space, we can abstractify. It's a word that I just created, I think. And say the following. Any set of operators which satisfy these commutation relations we think about as generating the algebra of a group of rotations. Okay? Now, there are different Lie algebras for the same group. That's a whole other story about the idea that things can locally look the same, but globally be different. For example, you know, displacements, a little displacement on a flat manifold here would be the same as whether I'm sitting on the Earth, which is a sphere, or in flat space, as people thought they lived, you know, out on the edge of Spain sometime in the 11th century. So there are different Lie algebras, I mean, the same Lie algebra for different groups. This is a Lie algebra for both two groups that we'll talk about a lot next semester, for two kinds of rotation groups. The group of rotations in 3 dimensions, the group SO3, and also the group of 2x2 unitary matrices that have determinant 1, the group SU2. Well, there's an intimate relationship between these groups. Talk more about that next semester. But for now, we just say, it doesn't really matter whether we're talking about SO3 or SU2. This is a Lie algebra. And we're going to just say, let's now consider the eigenvectors and eigenvalues of operators which satisfy this algebra. Okay? So, abstract. I'll call them J. Which satisfy the Lie algebra that we wrote down there. Okay. Now, we don't want to drag this darn H bar around with us. Oh, by the way, I should ask, what are the units of angular momentum?
Energy.
No, it's not quite. Not quite. It's momentum times distance, right? And that's the same units as H bar. Okay? So the units of angular momentum are H bar. And so we can just get, I'm going to get rid of the h bars by defining dimensionless operators. Now this is going to be the opposite convention, but whatever. I'm going to call the small letter ones to be the big letter ones divided by h bar. Okay? So that we don't have to carry around all those h bars. All right. We discussed last time, of course, that the magnitude squared of the vector, right, that's j dot j, that's jx squared plus jy squared plus jz squared. Given this operator, that operator commutes with any component. Okay. So what this means is that these two things mean that a complete set of mutually commuting operators is the magnitude square of the angular momentum and any one component. But not more than one of them. Okay? Could be the x direction, could be the y direction, it could be the z direction. We typically choose the z direction. We don't have to. Why do we only need two operators to completely specify the state? Well, that's a tricky question. If we go back to the case of the orbital angular momentum, that's clear. Because my Hilbert space associated with motion in 3D separated into motion along the radial direction and motion on the sphere. And in order to specify the sphere, that's 2 degrees of freedom. 2 degrees of freedom means I need two mutually commuting operators. And then we extract that out. Okay, so what we seek are the simultaneous eigenvectors of j squared and one component, and by convention we call the z-axis a special point. This is what's typically called the z-axis is called the quantization axis. It could be any axis we like, but because we define spherical coordinates with respect to the z-axis, that's where the theta is defined. That's just by convention how we define spherical coordinates. So that's why we chose it that way, the quantization axis. All right. So we see a set of eigenvectors such that I'll call the eigenvalue for now lambda of j squared and the eigenvalue of jz is m. Now we already know something about this, having done this. This was LZ in the context of orbital angular momentum. And we already found their eigenvalues. We just did it right over there using a differential equation, right? Just go back there for a moment. We saw just solving this equation, right? LZ on the eigenfunction if I divide by h bar is m times that. So those are the eigenvalues. And given this are the eigenfunctions, the boundary conditions tell us for orbital angular momentum the eigenvalues are integers. Positive or negative, but they're integers. Because it has to be the case that when I go around in physical space, 2 pi, I come back to where I was. So that means n has to be an integer for orbital angular momentum. All right, now to do this problem, it's natural to think about, we saw that the combination x plus iy and x minus iy played an important role in thinking about rotational symmetry. Okay, so we instead of just thinking about the x and y components, we think about the combinations x plus iy and x minus iy. Those played important roles, right? Corresponding to angular momentum around the z-axis. These, of course, we call j plus and minus. Of course, j plus and minus also, because any component commutes with j squared, a linear combination of components commutes with j squared. So that's true. Because x commutes with it, and y commutes with it. J sub x and j sub y. What about the commutation relation of, say, jz with j plus or minus? Well, that's equal to jz commuted with jx plus or minus I jy. And that's equal to jz commuting with jx plus or minus I jz commuting with jy. Okay? What is jz commuted with jx? You get to practice. IJY, most excellent. Cyclic permutations, right? And this one is
Negative
JX, super. Okay, terrific. So, this then is equal to plus or minus on this guy, plus or minus JX plus I JY, right? Which is equal to plus or minus J plus or minus. So the commutator of JZ with J plus or minus is equal to plus or minus J plus or minus. Okay? And it's a quick little exercise for you to show that the commutator of J plus with J minus is 2JZ. All right? So, with these commutation relations in hand, we can solve the eigenvalue problem algebraically using a method exactly like we did in the simple harmonic oscillator with raising and lowering operators. We already solved the Z angular momentum problem, LZ angular momentum problem with differential equations, but now we're going to do it algebraically. So first thing, we need a couple of little ansatz here. Let me make sure I have my notes here in case I forget something. Right. Okay, so we're going to have a few algebraic relations here. Okay, seems well. Let's look at j plus times j minus. That's jx plus ijy times jx minus ijy. And that's equal to jx squared plus jy squared plus ijy times jx minus ijx times jy, right? And this is equal to I times the commutator of jy with jx.
That's just JC, right? Negative JC.
So this guy, which one is this? Plus I or minus ijc?
Minus.
Right, this is minus ijz. Indeed. So that's plus jz. So this is jx squared plus jy squared plus jz. Jy squared. Okay. Now, jx plus jy squared is the magnitude squared minus the z component squared. Right? So that tells me that j plus times j minus is equal to j squared j squared minus jz squared, that's here, plus jz. Which is equal to j squared minus jz times jz minus 1. Yeah, that's correct. And similarly, if we looked at this other case, j squared minus jz squared minus jz, we have done it in the other order. So that's equal to j squared minus jz times jz plus 1. All right. Let's see. So now we can prove the following lemma. The claim is that it must always be true. So we're solving that eigenvalue problem where the eigenvalue of j squared is lambda, the eigenvalue of jz is m. And the claim is we can prove that it must always be the case that lambda is always bigger than or equal to m squared. Well, that's easy to prove. Let's look at the expectation value of j squared with respect to one of these eigenvectors. Right? This is lambda. But this is equal to jx squared plus jy squared plus jz squared. This is an eigenvector of jz with eigenvalue m. So this is this eigenvector, I'm sorry, this expectation value. Plus m squared, right? What about this number? Well, this is the expectation value of a positive operator. This operator must have positive eigenvalues. Jx squared plus jy squared is a positive number. So this is greater than 0, or equal to, because it's positive, not negative. Yeah?
Can we substitute like that jx squared plus jy squared is j squared minus jz squared, and then back those?
Yes, we can and we will.
Okay.
Yep. Absolutely. Right. Okay, so this is clear. This is greater than or equal to this, because this is always a positive number. Which means that for a given lambda, there exists a maximum m and a minimum m. Because m can never get too big, otherwise when you square it, it will start to get bigger than lambda. And it can't be too negative, because if it gets too negative, then when you square it, it also gets bigger than lambda. So for a given lambda, there's a maximum and minimum value of the m eigenvalue of jz. All right, next step. J plus and minus are raising and lowering operators. We kind of can guess that. I want to just back up for a moment. When we thought about the harmonic oscillator, and we were talking about rotations in phase space, we also had complex amplitudes, right? We had A was x plus IP, right? And that was the thing that allowed us to talk about complex amplitudes and was related to rotations in phase space. And it played the role of, the dagger raising and lowering operator. Well, now we have the same kind of thing, but now we're talking about not rotations in phase space, but rotations in physical space. So things like x plus iy kind of have the same kind of algebra as this. I'm waving my hands here. All right, let's prove it. It just gives us some motivation why that kind of maybe hangs together. All right, so the claim is that if I operate jz on the vector that I get by first, okay, that this operator is an eigenvector of jz with one more or one less unit of n. Okay? As to say, this vector is an eigenvector of jz with an eigenvalue that has been raised or lowered by one unit of n. Okay? That's the claim. Let me remind myself how to show that. Oh, yeah. Okay. Right. Yeah, we use the commutation relations, of course. That's what we do. So, hi, come on in. If you're like, yeah, it's either it's warmed up in here or I'm building up a sweat. I don't know. I do that all the time.
It's cold in here.
It's cold in here, yes. Thanks for looking at that, Gary. So, let's continue. We have written over there on the board the commutation relation between JZ and J plus and minus. So we need to move this through because we know how JZ acts on this, right? So this is equal to J plus or minus JZ plus the commutator acting on that, right? And this commutator is written over there. It's plus or minus J plus or minus. Okay? So, with that said, JZ acts on this. And what's that? JZ acting on this? M. Thank you. Because M acting on that, because this is an eigenvector of JZ with eigenvalue M. So this is M plus or minus 1 times J plus or minus acting on that. Voila! QED. Who doesn't like to write that down? Okay? So this is a raising the J plus and J minus act to create a new eigenvector of JZ with eigenvalue either raised by one value or lowered by one value. Okay? All right. So what we proved over here is that there existed a maximum and minimum value of the value of M. So let's consider the eigenvector keep writing that because we're going to do that in a moment. Okay, so that's the eigenvalue with the maximum value of M. The fact that there exists a maximum value, that's equivalent to saying that there is a state that I can't raise anymore. Because if I could raise it, it would be bigger than lambda. And the only way that's possible is that this is then annihilated by the raising operator. It's the only way. Otherwise, I would get M max plus 1, and it wouldn't have been a max value. Okay? Similarly, there is a vector which has the minimum value, and that must be annihilated by the lowering operator. Okay. All right. So now let's look at the action of the magnitude squared on, say, this guy. Let's consider this. Well, now we're going to dig out this lemma, which you say, why the heck did we do this? This is why we did that. Okay. So, this is equal to, let's see, one of these guys here. We want this guy. So I'm going to look at this, and that's going to be equal to J minus times J plus JZ times JZ plus 1 acting on that state. Okay? Just substituting that in. What is that equal to? Well, this is an eigenvector of jz with eigenvalue given here. So this becomes m max times m max plus 1. What happens to this guy when it hits this operator when it hits the k? 0. It annihilates it because we just said that. So this thus is m max times m max plus 1. So lambda is related to this maximum value of n. So the eigenvalue of j squared, which we call lambda, is equal to m max times m max plus 1. Moreover, we could do the same trick with looking at j squared acting on this guy. That's also lambda. So that's the state that has that eigenvalue of j squared lambda and this eigenvalue of jz. And now we use this other lemma. Plug it in, and we get this is equal to blah, blah, blah. J plus times j minus plus jz times jz minus 1 acting on this state. Right? And what is that? Well, this is m min times m min minus 1, and once again, when this hits this, it annihilates it. Because this is the minimum value, and you can't lower no more than the minimum. So that's m min times m min minus 1. So we have now a relationship that says the minimum and maximum value are related to one another like that. Oops. Sorry. Yeah, so far so good. So, the solution to that is to say that m max is equal to minus m min. If I substitute in here, m min is minus m max, I get that. Right? And we call that, we give that a name, we call it j. So, what this tells us, we've now solved the problem. J squared, so now I just call, so that tells me lambda is j plus 1. You know that. Instead of lambda, we call it, we keep track of j, that this is j plus 1. And jz is that. All right? We solved the problem algebraically. Of course, m for a given j there are a set of different m values that all share the same, or have the same value of j, right? So m goes from m max equals j to m min equals minus j in integer steps. How do we know they're integer steps?
Is it an integer?
Integer steps. Sorry?
M is an integer?
No, we don't have m as an integer. In fact, nothing tells us here that m is an integer. We know that m is an integer from, we know that we go in steps from this, that the raising and lowering operator changes the m value by plus or minus 1. These are the different states, all of which have the same value of jz squared. And how do we know that these all have the same value of j squared? That's to say, I claim that this I claim that j plus on this is an eigenvector of the magnitude squared with eigenvalue jj plus 1. How do you prove that?
Well, j plus lambda and max is 0, so plus or minus that will also be, or will be plus or minus 1, and that's an integer. And from there, it's just in steps of integer steps from there.
But I want to show that it's an eigenvector of this step, of j squared.
Don't they?
They do. That's the point. So j squared on j plus is j plus j squared, which is j plus 1 on j plus. So raising, and the same thing for the lowering operator. If you raise and lower, you don't change the value of j squared up until the maximum value annihilated. So we know that all of the states where I keep applying this are eigenvectors of j squared with different values of m, and we know that this is an eigenvector of jz with one more unit, and with a j minus, it's got one less unit. So that tells us from this fact that these are integer steps. Now, what are the possible values of j? Well, if I'm going to have these three facts true, that the maximum m is j, that the minimum value is minus j, and I get from the maximum to the minimum value through a sequence of subtracting or adding 1, then the only way that could be true is if either j is an integer or j is a half integer. Okay? So these two facts together tell us that j is a whole or half integer. Either of those will satisfy the eigenvalue equations. So, what we've learned thus is that we have these two equations. These are eigenvectors of the magnitude squared and jz, where m equals minus j plus 1, dot, 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 j minus 1j. And there are two j plus 1 values of n for a given j. Things you know. You just prove them again. Did you do the proof this way? Do you remember when you did some undergraduate quantum mechanics? You don't think so? Anyway, here's the proof. So, now, of course, to conclude this, what a beautiful work. God, this is genius. Look at this. Perfect, perfect. We just said this, that the boundary conditions for angular momentum insisted that we couldn't have a half integer. This wouldn't, if this were a half, then we went around 2 pi, that would be a half of 2 pi, which would be e to the I pi, which would be minus 1. And then the wave function would be discontinuous. So what this tells us is that relative to orbital angular momentum, things having to do with the motion of masses in space, that the half-integer solutions are not allowed. So the half-integer solutions not allowed for orbital angular momentum. But as we know, these half-integer solutions are still important physically. They have to do with intrinsic angular momentum that can't be thought of as the orbital motion of particles. And these are allowed solutions for spin. So this is spin only. There is no wave function associated with the phi coordinate of a particle for a half-integer angular momentum. It's not allowed. But there is an abstract ket that we can write down where j is a half and then m is plus or minus a half, which are perfectly allowed in quantum mechanics. Moreover, the whole integers can be either spin or orbital. We can have whole integer spins too. In fact, we saw one in your first exam, right? We didn't spin one. All right, we will continue this next time. Again, I won't be here, but I will be distributing the exams via email at 10 a.m. on Friday, tomorrow. And if you have any questions at all, please email me. Okay? All right. Study hard.